Okay, so let me first remind you the contents of the previous lecture. In the previous lecture, we talked about the, one thing that we talked about was the response. We are trying to understand the symmetry of the quantum Hall effects coupled to electromagnetic field and to the matrix. So I didn't give you the reference, but one place where you can look for formulas that I was giving in the previous lecture with maybe with a lot of error and sign error and factor of 2 missing is in that paper. Before going to these three topics, I'm going to remind you in a little bit in a different way what we did last time. So recall that we have a system of non-relativistic electrons. So it's assumed that we have quadratically dispersing electrons. And I'm going to couple these electrons to the electromagnetic field, part of which is the constant magnetic field that creates the quantum Hall effect. But we also assume that there is a perturbation on top of that magnetic field. And I'm going to put the system in a curve matrix. So I'm going to write down the action of such a system. So dt dx. And then now there is a Lagrangian density that I have to multiply that everything through the square root of the determinant of the metric. The metric is just G11, G11, G12, G21, G22. Is a two-dimensional metric. And then the proper scalar Lagrangian density, I over 2. So I'm going to be if pedantic and write this in a symmetrized way, the time derivative term, make sure it's everything's correct. So then I couple the system to scalar field, scalar potential, scalar potentials coupled to the density. And then there is a kinetic term for the electrons plus IAI psi EI EJ minus IAJ psi psi data. So it's kinetic term. And now I have a potential energy. So I have minus integral dt dx dy 1 minus 2. Then usually here I write the following. Usually we write the potential as a function of x minus y. But in the curve metric, we define, instead of x minus y, I would write the distance between the 2 points x and y in the metric G. So that's, I have 2 points, I connect that by a geodesic, measure the distance, and that would be my the parameter of the potential. And then obviously there is a x psi y, psi x. And here there's some factor of square root of g, that's g of x and g of y, make these. Okay, of course this is a play, this is a theorist play. It's, in principle, one can imagine trying to cook up the experimental system where we can couple the metric in such a way. The challenge would be to make sure that both the so here the interpretation of this term would be that we have a mass tensor that is anisotropic. This one corresponds to changing the Coulomb potential to a Coulomb potential in a medium with, say, spatially dependent dielectric constant. The challenge to cook up a theory, this Lagrangian, to make sure that these two things are correlated to each other. Let's assume that it's possible, that we are playing a theorist game. Try to do a Gedanken experiment and see what are the constraints that we can impose on the system. Okay, so now you can check, and let me write it down, the formula that the whole system is there is an invariance. Let me first write down the gauge invariance, and then I will explain in what it means. So invariance involves changing all the parameter in the theory by a small amount. So AI and Bj is equal to something that I'm going to write down. So for the metric, the formula is exactly like what we have in Riemannian geometry. So Gik Bj psi k minus Gk J Ei psi k. Psi is a parameter of the infinitesimal coordinate transformation, where x goes to x plus xi. And here I'm writing the passive version of this transformation. My coordinate system doesn't change, but all the field changes. Okay, so this is familiar. This one, Adx psi k, and then psi k to k 0 minus ik E0 psi k. Is one thing that I'm going to write in a different. So I'm not going to check that, but I'm going to explain to you what is the physical meaning of this formula. Usually when we when you read a popular book about Einstein's general theory of relativity, you see this Duncan experiment of a person in a folding elevator. So let's say there is the equivalence principle that generalizes the equivalence between different system of coordinates. Usually we say that a system of coordinates and a system of coordinates that constantly moving are equivalent. But general relativity extends that equivalence to equivalence between gravity. If you have a system with gravity, say if I'm saying here on Earth is equivalent to I'm in space, but in a spaceship that moves with a constant acceleration equal to g. Usually the description in these books refer to the extension of special relativity to general relativity. But another thing that one can do is another thing that people usually didn't think about is the equivalence between Galilean. It's that there is a way to extend Galilean invariance into a non-relativistic version of general coordinate invariance. So it happened like this. Suppose I have a system of particles with the same charge, E, and the same mass, M. Let's assume, what I need actually is only that the ratio of E over M is the same. So let's assume we have all these particular electrons. Now, I can go to the a system of coordinates that move with the acceleration. I can go to accelerated system of coordinates with the cost of changing the Newton's law. Usually Newton's law says that F is equal to ma, right? But in an accelerated system of coordinates, I have to add to the force a term that is equal to m times the acceleration of that system of coordinates, g. Suppose I'm going to a system of coordinates that move with a constant, or even time-dependent acceleration g of t. All I need to do to keep the law, the Newton's law correct, is to add to my force m times g. G is the acceleration. Now, if all the particles have the same charge-to-mass ratio, this m times g can be interpreted as an electric force coming from an electric field. E is equal to E. This mg is equal to E times E, where the electric field is equal mg divided by E. We can trade acceleration of the system coordinate with the electric field. So this is one way to make to formulate Newton's law in a way that makes all the system of coordinates equivalent to each other, not just system of coordinates that move with the same velocity. Now you can also do the following things. Let's go to the system of coordinates where we have a rotation. In a rotating system of coordinates, we have a Coriolis force. That Coriolis force is m2m omega cross v. Sorry, that's that correct? 2 of v times omega, one of the two. This Coriolis force has the same form as the Lorentz force, where this is the magnetic field. So there is a way to make Newton's mechanics generally covariant with respect to all coordinate system. So this transformation laws basically is the local version of the invariance of Newton's law with respect to any change of coordinate. We can go to a curved system of coordinates. We can we have to modify the transformation laws for the electromagnetic field. Last time we say that it's in the limit when m goes to 0, the transformation law is even simpler. So we can throw away this term. In case when the mass is 0, we don't have to worry, for example, about this Coriolis force. If we have a quantum Hall system in the lowest Landau level, we can go to the rotating system of coordinates, and we don't have to modify the magnetic field because the Coriolis force is very small compared to the Lorentz force in the limit of the lowest Landau level. Okay, so that's the qualitative things that I check.
Oh, so if I have some during the gallery there,
the whole picture is lost, but it's restored once you go to the lowest Landau level. So suppose I have a Dirac fermions. So all this is lost, but one can show that in the lowest Landau level there is an emergent symmetry that one can write up. To see that, one has to do some more detailed calculation. Okay, so now a proper summary of last time.
what is that? What's that? The great thing to not to understand the octopus still I say they're always the one. Just work out this with the say now what happening is on the call is sorry not see you gotta do it. Copy on how ask you this.
No, I'm not saying that. Maybe the more the better equivalence is in cold atom. People try to have been trying to create a quantum Hall system or create a magnetic field by rotating this cold atomic cloud. So you put the cold atomic cloud in a harmonic potential and then rotate the whole cloud with the velocity close to the critical velocity in which the whole system still is stable. And at that critical rotation velocity, the problem is mapped to a problem of particle in a magnetic field. One can trade acceleration in the system of coordinates with the electromagnetic field.
Well, so obviously they can like it to wall or
You can cancel out the magnetic field in that way as well. Yeah, if there is a microscopic magnetic field, and then if you rotate the system fast enough, then the electron will feel basically zero magnetic field. Okay, so last time we say that using this invariance, we can show that the quantum Hall's state, irrespective of whatever whatever the phase of the system we are in, has properties that one can, if we couple the system to A0 and Gij, and I'm going to perturbation theory over around the flat metric. Then the transformation for A0 and Hij looks like this. So if truly leading order in lambda, ignoring the nonlinear terms, epsilon ik ej dk lambda plus epsilon jk di ek lambda. The theory is invariant under this H symmetry. And we draw an analogy with Fredko's Higher-rank gauge here. We also said that if we have a gap system, if a system is gapped, then we can mentally try to integrate out on the gap degrees of freedom. For example, if we have electrons that becomes composite fermion, this composite fermion fill some integer number of Landau level, there is a gap. We integrate out the composite fermion field, and we should have an effective action written in terms of A0 and Hij that is not integrated out, that satisfy this symmetry. And then we say that the term that has the lowest number of derivatives that can be constructed from A0 and Hij that has this symmetry is a Chern-Simons-like term. So we create A0 times di dj Hij plus, here I'm writing two terms, but there is a relative coefficient between these two terms that I'm would ask you to fix. I will dot. Okay. There are two terms, and they have the overall coefficient is not fixed by the symmetry, but the relative coefficient between these two terms are fixed by the symmetry. So let's assume they are just 1 and 1. Okay, so some overall coefficient here, and there is a relative coefficient that we can find out. Okay, so here is I'm going to try to give you an interpretation of each of these terms. So term number 1, this term, what I want to interpret this term. Here I have written this term in the approximation of small perturbation over the flat metric, but if one do a full calculation, this term becomes A0 times the Riemann curvature of space. So R is the Riemann, the total Riemann curvature, which for around flat space, it becomes di dj Hij. By the way, here I'm assuming Hii is equal to 0. So this is a term that looks like the integral d3x A0 times R, and which means that when I compute the electromagnetic charge density by taking the derivative of the action with respect to A0, I get some contribution that is proportional to the curvature, Riemann curve, the Gaussian curvature of space. And if I integrate that rho of x electromagnetic over d3x, the contribution that comes from this term is equal to the integral of R over d3x. It's Euler characteristics. So that integral is equals, for example, 0 on the torus, and the Euler characteristic is 2 for a sphere, times the coefficient that it stands in front of this term.
It's a good answer.
It's a two-dimensional integral. The total charge is an integral over the 2x of rho. Thank you. And the two-dimensional integral of R is equal to 2 on the sphere. So this first term corresponds to a quantity characteristics of the quantum Hall state called the shift. And the shift is the following, it is defined like following. I compare two situations in which I have a quantum Hall physics on a torus and on a sphere. Okay, so I can put electrons in both cases. In one case, in both cases, I have to put some amount of magnetic monopole inside so that there is a magnetic flux going through the whole surface. So here I distribute the magnetic charge inside so that there is a constant magnetic field going through the torus. Okay, so on the torus, now let's consider a quantum Hall state, say with nu equal 1/3, for example. Then on the torus, turn out that the number of electrons is equal to nu divided by 2 pi integral of d2x in b, or just equals, I can write it's equal to n times the number of flux quanta through the system. In infinite space, that becomes just the filling factor is equal to mu, because n of phi is the number of state on the Lewis Landau level. So that one can ask about the sphere. It turned out that if one generalize the Laplace wave function on a sphere, one finds that the number of electrons is equal to mu and phi plus an offset, as we call S. And that S is the shift. So the shift is an extra number of electrons, the amount of electron, extra electron. The offsets in the linear relationship between the number of electrons and the number of flux quanta, fluxes through the sphere. And from this calculation, the shift is proportional, the coefficient in front of this term, A0 times di dj, the not T, has to be S. The coefficient in front of this term is to be S. So the first term in the effective action has the interpretation of the shift. Shift was introduced first by Wen and Z.
So there's just the counting bill. Instead, do you that mind the potential?
Yeah, it's a convention. And so, for example, in this convention, the shift for mu for 1/3 state, the shift is equal to 3, I think. Another for the Moritz state, I think the shift is also equal to 3. Moritz and say. Okay, so that is shift. Yeah.
But in real similar to the top, the button, how they know you take the audio pocket. Something close to the word. When
but if you realize on numerical experiment, typically you put like 18, 20 particle on a sphere, and then you ask how many flux quanta have to put it through the sphere for that, so that there is a gap like in your 1/3 state.
Restricted is like is this something you measure that comes out of the
No, experimentally I've never seen it measured, but it's the properties of, we know that it's a property of the quantum Hall state. So a more closer thing that is measured, yeah.
You said how you process to.
Yes, so I'm going to, so directly measuring this offset is on a sphere is a challenge, because you have to put the system on the sphere and then measure. Yeah. But now I want to tell you that it's related to this coefficient of the H times Hij dot term. So there are two ways to think about this term. One is, yeah.
I would actually develop hours to the because the it can't go ahead. It more money.
No, you're not misunderstanding. Suppose I'm doing this composite fermion, and think about the composite fermion on the torus. There's no problem on the torus, right? You attach three fluxes, and then you get everything correct. Now you can ask, suppose you attach fluxes here, then you find that suddenly there is because the number of electrons is not exactly equal to 1/3 of the number of flux quanta, there is a flux quanta left. And where does it come from? It's actually related to the spin of this composite fermion. The composite fermion has a spin. And if you have a particle that carries a spin and it moves on the sphere, there is a Berry phase when it moves on the sphere because the direction of the spin has to change. So a spin effectively means that there is a effective magnetic field coming from the curvature of the sphere, and this thing and the remaining magnetic field conspire to cancel each other and give you the composite fermion in the average zero magnetic field. No, the shift doesn't have to be. I know for 2/3 state the shift is zero. For 3/5, I think starting in the chain sequence of approaching 1/2 from above, I think it's become more and more negative. Go from 3/5, 4/7, etc. Become more and more negative. In fact, yeah. Okay, so any question?
Yes, thing that you're talking about.
You have, yeah.
Top of your stomach.
Can discuss that. I think it's maybe related in some sense to a real spin. It's not exactly a real spin. Okay, so the second term, you want to understand this one. There is two ways to think about this. One as a Berry phase. So let me try to draw for you picture of this. S now equal integral of d3x Hij dot epsilon jk. Okay. So recall that I have a 2x2 matrix H11, H12, H21, which is also equal to H12, and I have H22, which is equal to minus H11, because I assume my metric perturbation has a zero trace, or the total metric is determinant equal to 1. So suppose I forget about the spatial dependence of H and think about only the time dependence. So here I can draw a space where on one axis I have one H12 and the other axis I have H11. Right? And let me assume that I changed my metric in such a way that I make like a closed curve in this on this H11, H12 plane. This term is like PQ dot term in quantum mechanics. That is, the system will, the ground state after this transformation will have a Berry phase that is proportional to the area enclosed in this region. So one way to think about that is that's related to the Berry phase of the ground state. Okay, but in principle, that's one way one should be able to compute these terms if we know the wave function of the ground state in curved metric of, not even in curved, but in constant metric H1 and H12, one should be able to compute this. It's probably possible to do, but it looks complicated. But another interpretation that maybe more physical is that we have in the time-dependent metric, we have a stress tensor, and you write Hij equal to epsilon ik hkj dot plus epsilon jk hik dot times some coefficient. So this implies this coefficient is the whole viscosity. The way to think about this is to think about the change of the metric as one can make this not just the analogy, but a more precise statement that we have set up in the system of flow that would move one part of the fluid with respect to the other. So if I have, say, H12 dot not equal to 0, that correspond to setting up in the quantum Hall fluid a flow with the velocity that goes linearly along, say, the y direction, and the whole flows in the x direction. You can think about that as if you draw a volume that is square in the beginning, with time it will become more and more like that, and that would correspond to H12 dot not equal to 0. So here we have, if we set up a flow like this, we get a stress in the x, in the 1 direction is equal H12 dot. So in the usual fluid, if you set up a stress that the shearest in the 1-2 direction, you get a component's contribution to the stress tensor also in the 1-2 direction. But here everything's rotated by 90 degrees. And so that is called the whole viscosity, or it's called the hot viscosity. You can find the hot viscosity. And we have seen, because in the Lagrangian there are two terms that are related to each other by the requirement of the gauge symmetry, the whole viscosity or hot viscosity is proportional to the shape. That I'm not going to write the exact proportionality coefficient, but if we know the shape, we know the whole viscosity. The proportionality coefficient is just density divided by 4. So. Any question so far?
Hey, this stuff is what I check not to you do make that.
Yeah.
You think then with the math for that your business was it then that's
it's going to be not that I'm not sure if it's there is a precise correspondence between the one can imagine, suppose I have an electric field in this direction, I get a stress in this direction, that corresponds, but I get a flow that has this this pattern, and then that corresponds to extra pressure on the quantum Hall state in the XX direction. How to convert that extra pressure into a measurements that say related to the charge distribution near the edge. I think it's not that direct. It's not clear. But there is a way to derive another relationship. There is a relationship between the Q dependence, the dependence of the whole conductivity on Q that involved the whole viscosity. But in order to derive that, I have to go a little bit further into this gauge invariant. So now that is equal to QH0 plus Q square, and the coefficient in front of this Q square is equal to, is related to the whole viscosity of the shape. So, but that is the using the gauge symmetry that I presented, one can derive this relationship. Okay, any question?
I think that comment related to Shane's question. So they tell farmers that we think for the thing with sanitary doctors, the bacon ship, they're nice of moment. Secondly, it's also the first year the side of the soil. There's about what
that I think is
I pull in it. Because that's the not standing with so 16 and not for your school. That's you know, exactly like we actually worked about. Basically, there's some something here about this. I do, yes, it's still bright at this. So it's in that sort of people cutting spectacular have it. I think it's in West Hand and three of them. It's a
universal until proven otherwise. Okay.
Just want the point, you know, that, but you did this all for the case for your iron tobacco stick. So lead there, saying that and get sun from to continue following for to sort of this, but it's symmetry allow sharing the part of relativity. Or with one kind of square thing, the cut to that thing, but that's the thing.
Because it's compressible, I'm not sure if I can do anything. I haven't derived anything. Yeah.
It won't be plot size for the bank, and it's just like the fluid dynamics and what is.
There could be, yeah. I'm not sure. I'm not sure I know. Yeah, I know. For example, I can ask the same question about finite temperature quantum Hall. Is there a relationship between viscosity or this? I'm not so sure that there isn't. Probably there is.
But that's that. Please, this is not true. But done that the like a contest. Register was significant, and that could sit
yeah, if it's symmetric, if it's particle Hall symmetric, then the guiding center contribution to the whole viscosity is 0. So it's the whole viscosity is just equal to the whole viscosity of the field Landau level times mu. Yeah. If it's particle Hall, yeah.
All of the dealing on the second big should be also so you can get about the actual value, but the cost from low and jack it out this.
So let me formalize this notion of the whole viscosity as a statement about the 2-point function of the stress tensor. So if I take the stress tensor and if I compute 2-point function Tij TKL, right? And I can do a Fourier transform. And let me put the momentum to 0 just for simplicity. Momentum to 0. Now it's a function of omega only. Now there are 2 possible structure consistent with rotational symmetry that I can write down. Ck plus the IL with Ck minus, I think that JD they times. Let me call that coefficient. How do I say? Let's call that f of omega, and then there's another one, Ik epsilon JL plus delta JL epsilon ik times another, say, function g of omega. Then the whole viscosity is the limit when omega goes to 0. That is omega much less than the gap. G of omega goes to saying something like omega I omega times the whole viscosity. That's how the and the whole viscosity can be, this function, it can be defined to all omega. So this, I plot the function g of omega, it will be linear here with a slope. I'm not sure if there is an I, it depends on the convention. It's linear here with the coefficient equal to the whole viscosity times omega. And now I can actually ask about the behavior of this function at high frequency. Is omega much larger than the gap? So here omega much less than the gap. And omega is much larger than a gap, then the response of the guiding center, well, let's say much less than a gap, but still much smaller than h bar omega c at the cyclotron frequency. Right. So in the lowest Landau level limit, there is a nice regime that one can take when we probe the system at the frequency that is still we still leave a system on the lowest Landau level, but we can probe it with frequency so that the guiding center doesn't have time to react on it. So in terms of the guiding center, it is the guiding center simply stay in place. The wave function of the guiding center doesn't change. The only thing that changes is that the shape of this Landau orbit changes with the metric. And one can show that here the behavior of the function omega is also linear, but with some coefficient that has the meaning of the whole viscosity at infinite frequency. The whole viscosity of infinite frequency turn out to be just proportional to, is equal to nu times the whole viscosity of a full Landau level. That's like as if every electron has its own Landau orbital that react independently from the other electrons. That's why the whole viscosity is equal to this omega. Okay, so now I can write down some kind of a sum rule. The sum rule is based on the analytic properties of this function. It's basically a Kramer's chronic type of relations. One can show that the change of the whole viscosity from 0 frequency to infinite frequency is related to the integral of the omega over omega squared to infinity times the imaginary part of this function g of omega. Fine. Sure, it's probably here it's a real it's a real part. So this is a relationship between real and imaginary part. So using the relationship between the shift and the whole viscosity, one can show that this one is equal to shift minus 1. Proportional to shift minus 1 times the field, I think times the feeding factor here. Up. I think it's I think the real part goes to a linear function, and the imaginary part can be argued to be smaller from the real. So in there's some convention that I cannot figure out online. Yeah.
This is the server. But
How do I measure I can define, but I will tell you how approximately one can measure, but one can define this 2-point function theoretically. Measuring it, again, we need to couple the system to gravity, and then so let me give you a thought experiment. Imagine that you have a source of gravitons. You shine the source of graviton to the system and measure the absorption of the graviton by the system, and that would measure this imaginary part of this co-function. Okay, so this sum rule, and one can also show the following things that we have in your previous lecture. We have derived the conservation law for the density. We kept a relationship that relate the density with the stress tensor that looks something like this. Epsilon jk ti k plus ... is equal to 0. So, and using this thing, you can relate the dynamic structure factor that is usually called SQ omega. Which is the SQ omega is the imaginary part of the 2-point function of rho. Right? It's equal. It turned out to be equal to q to the 4th divided by omega squared times the imaginary part of the function f. You can mentally see where it comes. Q to the 4th comes because rho is equal q squared divided by omega of t, roughly. Rho roughly q squared over omega of t. So 2-point function of rho, which is the dynamic structure factor, give you the imaginary part. So here I take q goes to 0 limit so that I can ignore the q dependence in the function s. So from that, we can show that the coefficient in the static structure factor that is S of q is equal integral d omega S of q omega. The static structure factor is something that one can read out from the wave function, is equal q to the 4th integral d omega over omega squared imaginary part of f omega. So these two formula looks very similar to it. Static structure factor as q goes to 0. In fact, to be precise, it's a projected. The projected static structure factor has a q to the 4th behavior at small q. That is something that's known already from Kirby, McDonald, and Flaxman. But it's the coefficient of q to the 4th has a relationship between the imaginary part of one of this function in the 3-point function of t. Now, there is one more relationship, now more like an inequality. So now one can show f is larger than absolute value of g. In fact, one can show that f minus g and f plus g both have to be larger than 0. The way to show that is to interpret the imaginary part of f is larger than the imaginary part of absolute value of imaginary part of g, or imaginary part of f minus g and f plus g both larger than 0. And the reason for that is that both this imaginary part of f minus g and f plus g both can be written as something that is manifestly positive. So this one is integral is the sum over all intermediate state. Because it's a two-point function, imaginary part of two-point function is some kind of spectral density. So it turns out that f minus g is the spectral density of the operator that we can call tz bar z bar. So here I'm writing it. I'm not sure which one is which, but imaginary part of this f plus g or f minus g is sum over intermediate state of the matrix elements of the operator tz bar z bar. That tz bar z bar basically is an integral over the whole space of the components of the some components of the stress tensor T11 minus T12 plus say I2I T11 T12 etc. Because the matrix element here is squared, in absolute value they have to be larger than 0. And so this allows us to show, using this inequality, we now find that the limit of S Q divided by Q to the fourth, Q goes to 0, but S of Q is the projected static structure factor is larger or equal, I think, S minus 1 divided by 8 or something. So this is, sorry for the notation, this is the shift, and this is a static structure factor. And this was the relationship that was first derived by Holding. It's an inequality that should be valid for all quantum Hall state. And it turned out that it's saturated by Laplace wave function. And we compute this Laplace, the S of Q Laplace wave function. It's actually the inequality. This just becomes an equality.
But it's also typical a certain part that the integer point phase. Yeah, I think the young man.
I'm sorry. For integer quantum Hall state, the projected structure factor is 0, and then that is And actually, let me write this is absolute value of S minus 1 divided by
so
A. Okay, so now the last one is the spin 2 mode in the quantum Hall class.
It's like how did I said if the thing is like but to go actually the surgeon.
No, it's only valid at the lowest Landau level. Yeah, it's all have to be lowest Landau level. Okay, so the sum rule tells us that there is relationship between the imaginary part of this odd part of the Green's function for stress tensor. The simplest way to satisfy is to assume that this imaginary part has a delta function at some omega 0 of order the gap, and this f of g of imaginary part of g of omega is equal to that delta function. This integral is saturated by a single pole. Okay, it's not guaranteed that we always have this, but this is one simplest possibility. Suppose we take that to be we assume even more than that, that we assume that this Haldane inequality is almost satisfied. That is actually an equal sign here. Then one of the only one of the spectral combination of F and G is non-zero. The other one is zero. So let's assume that the first one is F equal to G, and so the first, in order to saturate the Haldane bound, F should be equal to either equal to G or equal to minus G. So one of these, the imaginary part is equal to zero. Let's assume this is equal to zero, and this is not equal to zero. Then what we find here with these two assumptions is that this peak is then a quasi-particle that is created by the operator, say TZZ. So we have a quasi-particle. This peak in the imaginary part of G correspond to a quasi-particle created by the operator KZC act on the vacuum. So is it a new particle or is it an old something that is known before? So I claim that this is nothing but the old magnetoroton, but at Q is equal to 0. So the Gervin-McDonald and Platzmann magnetoroton dispersion relation is usually drawn like this. In fact, there is an argument that this will have to saturate to a constant epsilon at Q, and this is a function at Q. Gervin-McDonald and Platzmann. One way to think about the magnetoroton is that it's a bound state of a quasi a Laplacian quasi-particle, say with charge E over 3 and charge minus E over 3. So it's probably a good picture for the magnetorotons at very large momentum. But at zero momentum, we found that this has to be, since something must saturate the sum rule, this has to be a particle with spin 2.
Then why do you take the thickness and boxed up to stick?
Why do I have to assume that there is a
Insipid. Why right?
In fact, I'm not. It's probably too strong. If I assume that TZZ, one of this function is 0, that means that the imaginary there is no particle created by TZ bar Z bar acting on the vacuum. Give me just 0. Yeah, it's actually the property of the Laplacian model, the Hamiltonian of the with the only V1 interaction, that TZ bar Z bar acting on the vacuum is 0. So, but I have I can argue that there is such a mode with less assumption. So these magnetorotons then have to have a spin equal to 2, and that's actually something that wasn't known when Gervin-McDonald and Platzmann wrote their paper. They were trying to Gervin-McDonald and Platzmann tried to create this mode is by acting a projected density to the ground state. And if you look at their this wave function, it becomes less and less. There is less and less weight as you take Q goes to zero. When Q goes to zero, the overlap with the single particle excitation become much less and less. And that's a consequence of the fact that this operator has a wrong spin to create a spin 2 quasi-particle at Q equal to zero. It's much more efficient to create this quasi-particle by using an operator that carries properly a spin 2 operator, which is a component of the stress tensor. Yes, so in finite momentum, the notion of spin becomes more fuzzy because, suppose I have, you look at the quasi-particle here, you can talk about the total angular momentum, which is x times k plus s, right? But the you have to know the center of mass of this quasi-particle to say what is it angular moment. It's that orbital angular momentum. And so the notion of spin is well defined at Q equal to zero, but become less and less well defined as you go away from your Q equal to zero. Mathematically, Q equal to zero is invariant under rotation. So the only contribution to the transformation of the quasi-particle is in its spin. Okay, but if you're close to here, the particle would still have spin equal to 2. I don't have any time, so I will just tell you the experiments where it's all theory, but now one can ask whether one can measure in experiments the spin of any of this quasi-particle, and it is done through Raman scattering, as I mentioned in the previous time. We shine photons to the system and observe a photon with energy that is slightly less than the energy of the photon that come in. This delta is going to be the energy of the quasi-particle that is created. But we know that photon has spin. So if we prepare a beam that corresponds to one circular polarization, that will correspond to a beam of photon with some projection of spin Sz in, and then the Sz out. The difference between the incoming Sz and the outcoming Sz of the photon is the spin of the particle that is left on the system, and that's how one can determine the spin of the photon. It's turned out to be 2 in the recent experiment, either plus or minus 2, depending on nu, on exact quantum Hall state, and the sign of the spins also correspond to the sign of the whether the ship is larger than 1 or less than 1. So that experiment was done at Nanjing University by Lin Xidu and his collaborator. So this is a photon spin. So photon spin is plus or minus 1. This one's plus or minus 1. And so by using the fact that the projection of the photon spin on the z-axis can change, one find the spin of this neutral quasi-particle. Okay. Thank you very much.
Probably just take your question and I think the loss of judgment. Right. Just do it. And they don't get it and it's really
It's not X-ray. Here it's just optical. It's more optical. It's laser. The energy of that photon is about 1 MeV. 1 EV. I'm sorry, 1 EV. So it's more or less visible optical photon.
Did that make any sense? Yeah.
There is no phonon here. There's no phonon. One is permitted.
In principle, the photon is that some mechanic, but it grows efficient to where photon matches the that you can way of stand measure that the optimism.
Yes. So the
That's why we do there's the one and top.
yes. So experimentally, what people do is to tune the frequency of the gamma to be equal to the band gap in gallium arsenide.
Bolden. Nice. Be like that. You will.
No, it's much larger. So this energy is much larger, but the difference between the energy of the incoming and the outgoing photon is a milli electron volt.
Yeah.
Yes.
The one question. So it's still in the
It is a real spin. It is a real angular momentum. So the system of particle have if there is a rotational symmetry because this electron here is quadratic dispersion, and so it's a real angular momentum of a quasi particle.
So that's like in the yeah.
Well, if there is only discrete symmetry, then the angular momentum is not conserved. So it's only conserved up to, say, 4 in the case of a square lattice, or 6. There is better. In principle, there must be a notion, if there is a quasi-particle that we can put at rest, the state of that quasi-particle should transform under discrete rotation symmetry. And one can ask whether that quasi-particle has a spin 1 mod 6 or mod 4.
But when saying you have been managed to have the data straight and have starting seeing the more cheaper and system is hey, well, I guess sort of it's a pill like to make some else for some of the revenue move on to the well, I think there.